All right. So today we're going to be talking about balanced three-phase circuit analysis. And we're going to start by looking at a simple YY system. So give me just a moment and I will draw said system out. All right, so I'm going to start by giving myself a Y-connected voltage source over here on the left. So this will be our phase voltage VAN. My A phase terminal for my source. Here's VBN, my V phase terminal. VCN, my C phase terminal, and I am explicitly going to include a neutral conductor in this system as well. So here is my neutral terminal. So here's my voltage source. Over here on the right-hand side, I'm going to put my three-phase load. And I'm going to call the A phase impedance ZYA, the B phase impedance ZYB, and the C phase impedance ZYC, like so. And lastly, I'm going to connect my source to my load with a transmission line segments, each of which will have some impedance as well. So for the A phase, I might call this ZWA. In the B phase, we'll have an impedance ZWB. In the C phase, we'll have an impedance ZWC. And my neutral conductor will also have some impedance, which I'm going to call Z sub N, like so. All right, so here's my simple generic YY system. And the first thing that I want to discuss is under what criterion this system can be considered a balanced three-phase network, okay? So let me write down here. Criteria for balance. So we're going to start on the source side of things, okay? So our first criteria is that the magnitude of the phase voltages at the source are equal. So this means that the magnitude of voltage VAN is identical to the magnitude of the source voltage VBN is identical to the magnitude of the source voltage VCN And so I'm going to call these quantities VP RMS. So we're just representing everything with some effective value in RMS voltage. And I'm just going to call that my RMS phase voltage for the entire system. Okay. So that's the first criterion. The second criterion is that the phase separation between the voltages at the source is 120 degrees. So by this, I mean explicitly, we're going to be dealing with a positive phase sequence system. So the phase angle theta Bn, which is the phase angle for voltage VBN, must be theta An, the phase angle for phase voltage VAN. Really, it would be plus or minus 120 degrees, but because we're dealing with a positive phase sequence, I'm only going to choose to include the negative sign here. And on top of this, theta Cn must be equal to theta An minus 240 degrees. And once again, this realistically could be plus or minus 240 degrees. But because we're only dealing with a positive phase sequence system, we're just using the negative sign. So under those two criterion, our source is a balanced thing, okay? Now, let's talk about what makes the transmission line network a balanced thing, right? So we need our transmission line impedances to be equal. So specifically, that means that the quantity ZWA must be equal to ZWB, must be equal to ZWC, and we'll call this just some impedance representative of our transmission lines. Now I want to point out here, we do have a neutral conductor represented by that impedance Z sub N. That is effectively a transmission line as well. However, its value does not have to be the same as the A phase conductor, B phase conductor, or C phase conductor. This is actually reflected in the National Electrical Code, or the NEC. So there are very specific requirements for the phase conductors. The neutral conductor can typically be a smaller sized conductor, so less copper and therefore cheaper. And the reason is that the neutral conductor should carry significantly less current in the network. So the neutral conductor is responsible for carrying the imbalance in the system effectively. And in a balanced three-phase network, as we'll find out here in a couple of minutes with some mathematical analysis, it will actually carry zero current. So we'll find that the neutral conductor actually carries no current and therefore has no voltage drop across it in a balanced three-phase system. And this is one of the fundamental points of a balanced system that actually makes it very easy to analyze. Unbalanced systems are much, much more difficult to look at. Okay. All right. Absolutely. So the transmission line impedances are equal. So let's talk about what that means from a practical standpoint, okay? It means realistically that you're using the same size of conductor and you're using the same length. So if we're talking about transmitting power over a long distance, effectively the length of each section of transmission line is going to be the same because the distance between the poles that the lines are mounted on are the same. So it's kind of hard to not have the lines be the same size and the same length and all of that kind of stuff because they're installed at the same time, usually from the same spool of cable. So It's incredibly regular for the transmission line impedances to be virtually identical. Okay. The imbalance in a three-phase system is usually going to be here on the load side of the system, which we're about to talk about. So in order for the load to be balanced, the load impedances must also be equal. So that means that impedance ZYA is identical to ZYB is identical to ZYC. And so we can represent all of these by a single equivalent impedance ZY. Okay. So these are our constraints for a balanced system, and we will bring them up as necessary. Okay. So what we are going to do is we are going to look at our line currents here. Okay, so I'm going to draw them on my diagram. Line currents, as we learned last lecture, are just the currents that are flowing down the transmission line from the source to the load. So we're going to have a line current IAA on the A phase, a line current IBB on the B phase, a line current ICC on the C phase, and we're also going to have a current INN on the neutral conductor, like so. Okay. So we are going to make an assumption here, and this is an assumption purely for calculations sake. Okay, so in a real three-phase system, there's usually not actually a ground, but we are going to consider the source side neutral to be at ground. We're literally just using this as a reference. Okay, so this is an analytical ground, not necessarily a physical connection to ground. Okay. If we do that, then we can apply Kirchhoff's current law to the rightmost node, which is the load side neutral. And what we'll find, so let me write this down here. So applying KCL at the capital N neutral terminal, we should see that all four of our line currents add together to make zero. Right? So IAA plus IBB plus ICC plus INN are equal to zero. And now what we're going to do is we're going to use Ohm's law to express all of these currents in terms of voltages. Okay. So the current IAA is the current that's flowing through the series impedance ZWA plus ZYA, right? So I could express IAA as voltage VAN. So that's where the current is starting from. It's flowing to the node VNN divided by ZWA plus ZYA. So I want to be clear that we're all on the same page, okay? So the voltage VNN would be the potential difference between the rightmost node and the leftmost node, like so. So realistically, all I've done is just drawn effectively a little KVL loop around this path, starting and ending at ground, to find the total voltage drop across that series impedance, and then divided that voltage by the impedance to give me current. So just application of Ohm's law. Okay. We all okay with that? No black magic or hand waving going on in here at all. I'm going to repeat that for the other line currents, right? So we'll have plus VBN minus that same voltage VNN over ZWB plus ZYB plus VCN minus VNN times ZWC plus ZYC. And then I'm just going to warn you right now, I'm about to write something down, and then I'm immediately going to change it. So maybe don't write it down just yet. Okay. So the voltage drop across the neutral conductor is going to be V lowercase n capital N divided by that impedance Zn. And now what I'm going to do is I'm going to flip the subscript on that neutral conductor voltage so that it's V capital N lowercase n. So that's literally the exact same voltage that we have in all of the other terms. So when I change the subscript order, that's effectively the exact same thing as me multiplying by -1. So I'm going to change that plus sign into a minus sign, and now I'm going to have V capital N lowercase n and set this equal to 0. So right now, everything is expressed in generic terms for any type of YY system. Now let's start imposing that the system is balanced and see what shakes out. Okay. So for a balanced network, this equation will reduce to, so I'm just going to move that last term over to its own side of the equal sign. So I'm going to have V capital N lowercase n over Zn, that should be capital, is equal to VAN minus VNN over ZW plus ZY plus VBN minus VNN over the same ZW plus ZY plus VCN minus VNN over ZW plus ZY. And now I'm going to move all of the VNN term. Isaiah, did you have a question? Yeah. Okay. So now I'm going to move all of the VNN terms over to the left-hand side of the equal sign, right? So that's going to look like VNN times 1 over Zn plus 3 over ZW plus ZY is equal to VAN plus VBN plus VCN all over ZW plus ZY. And now let's consider what happens when our source is balanced, right? So this is kind of an aside thing here, but for a balanced source, VAN plus VBN plus VCN is going to look like VAN plus VAN multiplied by 1 angle negative 120 degrees, because we know our B phase has the exact same magnitude as our A phase. It's just shifted by negative 120 degrees. And similarly, our C phase can be represented by VAN times 1 angle negative 240 degrees. So lumping things together, this looks like VAN times 1 plus 1 angle negative 120 degrees plus 1 angle negative 240 degrees. So I would like for somebody to put this bit right here into their calculator and tell me what comes out. Zero. Okay. So that means that all three of those phase voltages added together is going to be zero for a balanced system. Okay. So coming back up to this expression, I'm just going to put this as equal to zero. What is the implication here? Well, VAN, VBN, and VCN individually aren't zero. Those are our source voltages. But the left-hand side of this expression and the right-hand side of the expression have to equal zero. So that means that if 1 over ZW plus 3, or excuse me, ZN plus 3 over ZW plus ZY is non-zero, which it should be if there are any impedances in our system, the only thing that makes this work is if the voltage drop across our neutral conductor is zero. Okay? So from here, we can say that the voltage VNN must be 0 volts. This is a very important thing. Okay? So if the voltage drop across our neutral conductor is 0 volts, then from this, we can say that the current flowing down our neutral conductor is negative VNN over ZN is 0 amps. Okay? So no voltage drop across our neutral conductor, no current flowing through our neutral conductor. Let's look at our other currents, right? So let's look at our line current IAA, right? So VAN minus VNN over ZWA plus ZYA in a balanced three-phase system is just going to look like VAN over ZW plus ZY. Our line current IBB for a balanced three-phase system, let me write this out here, WB plus ZYB is going to look like VBN times, excuse me, divided by ZW plus ZY. which is the same thing as VAN times 1 angle negative 120 degrees over ZW plus ZY, or simply IAA times 1 angle negative 120 degrees. And we can do the exact same treatment for ICC. So VCN minus VNN over ZWC plus ZYC. I'm going to skip these intermediate steps. Is going to look like IAA times 1 angle negative 240 degrees. So in our balanced system, what we have just observed is that all of our line currents are identical in magnitude, but separated in phase by 120 degrees, just like our source voltage, okay? So that's a pretty important thing, but we can take this a couple of steps further, right? So I want to look at our line voltages here really quickly. Okay. So let's look at this voltage. VAB, this voltage, VBC, and we could also have a voltage VCA, which we'll get to in a moment, right? So if I were trying to figure out what this line voltage is, I could write a KVL equation to figure things out. So what I am suggesting is that that voltage VAB will be this voltage VAN minus this voltage VBN. And while we didn't explicitly state anything regarding this just yet, that voltage V capital A capital N and that voltage V capital B capital N, the magnitudes of those voltages have to be identical because the same current is flowing through them, same magnitude of current is flowing through them. So those voltages are going to have 120 degrees of phase separation between them. And what we're going to see is that the phase voltages will all be separated by 120 degrees. And when we do a little bit of math here in just a moment, our line voltages are also always going to be separated by 120 degrees, right? So let's play around with that really quickly. Okay. So just looking at some things here. So VAN, by definition, is going to be IAA times ZY. VBN is going to be IBB times ZY, which is the same thing as IAA times ZY times 1 angle negative 120 degrees. And VCN is going to be ICC ZY, which will be the same thing as IAA ZY 1 angle negative 240. Sure. Okay. So I'm actually going to put a quick note here. So phase voltages at load have same magnitude and 120 degrees phase separation. So the voltage VAB is just VAN minus VBN. We're accidentally going to stumble into a transformation here that we're going to wind up using in a few minutes. So this looks like VAN minus VAN times 1 angle negative 120 degrees, or VAN times 1 minus 1 angle negative 120 degrees. Somebody tell me what 1 minus 1 angle negative 120 degrees is, please. Taking too long, it's √3 angle 30. If we did VBC, this would be VBN minus VCN, which could be expressed as VBN minus VBN 1 angle negative 120. And using the exact same logic, we would then see that this is VBN times √3 angle 30 degrees, which is the same thing as VAN √3 angle 30 degrees, also multiplied by 1 angle negative 120 degrees. So we're going to wind up having same magnitudes and 120 degrees phase separation for all of our line voltages as well. VCN would be VCA, VCN minus VAN, which is going to look like VAN √3 angle 30 times 1 angle negative 240. So putting all of this together, line voltages have equal magnitudes and 120 degrees of phase separation. So why I'm bringing this up is because realistically, all of our quantities are going to have, so all of our line voltages, whether it's at the source, so all of our source line voltages will have the same magnitude, 120 degrees of phase separation. All of our load line voltages will have the same magnitude, 120 degrees of phase separation. All of our line currents will have the same magnitude and 120 degrees of phase separation. All of our phase currents will have the same magnitude and 120 degrees of phase separation. So realistically, if I can figure out what a single phase is doing, then I know what all of the phases are doing because I just shift my result from that first phase by 120 degrees. I don't have to ever do analysis on the entire system. I can look at it on a phase by phase basis, okay? So let's talk about what that would entail by using what's called a single phase equivalent circuit. So we know that in a balanced YY system, the voltage drop across the neutral conductor is 0, and the current flowing through the neutral conductor is 0. Since there is no voltage drop across our neutral conductor, we can treat the neutral conductor as if it were a short circuit, regardless of what its impedance is, even if it's an open circuit, meaning the conductor does not exist, we can still treat it like a short, okay? So that allows us to subdivide a balanced YY network into 3 independent single-phase circuits. So what we would have is something like this, okay? So here's our voltage VAN. Here's the lowercase a terminal. Here's the lowercase n terminal. Here is our impedance ZW. Here's our uppercase A terminal. Down here is our uppercase N terminal. Here is our load impedance ZY. And then there's our neutral conductor. So let me put the B phase circuit here. VBN. ZW. ZY. Should have been lowercase n. Lowercase b, uppercase b, uppercase n. And over here on the far right, BCN, VW, ZY, so now let's talk about what quantities we can determine from analyzing these incredibly trivial single phase representations of each phase of our circuit, right? So I think it's fairly obvious that we should be able to figure out what our line current is. And I think I'm using the right color here. I apologize if I'm not. What our phase current through our load is. And if we know our phase current through our load, it should be pretty darn easy for us to figure out. Or that should be lowercase. The phase current through our source as well, because that's just going to be the negative of the phase current through our load, right? We should also be able to figure out the phase voltage across our load. We will not be able to figure out the line voltage across our source or the line voltage across our load from this circuit, okay? Not directly, anyway, okay? But as we kind of showed up here, there's a pretty easy transformation that we can get, okay? So let me find an example here. Yes. Correct. So excuse me, I can't talk today. We're literally going to put this into practice here in a moment to explain kind of how powerful this thing is, okay? So let's say that I have the following circuit that I'm trying to analyze, okay? So I'm going to have a simple balanced YY system. This is going to be a three-phase, three-wire system, so I'm not going to explicitly include any neutral conductor. So here's A, B, and C. Here's my transmission line impedance ZW. And then over here is my load, ZY. And let's say that we are provided the following information. Let's say that our voltage VAB is 277 angle 30 degrees volts RMS. Let's say that ZW is 0.1 plus J 0.05 ohms. And ZY is 5 plus J2 ohms. And I'm interested in determining my line currents as well as my line voltages at the load. Let me go ahead and explicitly draw these line currents as well. So we're going to talk now about how to use our single phase equivalent circuit to find the information that we can directly, and then how we can indirectly find our other quantities, okay? So first things first, I'm going to draw my single phase equivalent circuit, and I'm going to figure out if I have any missing information, and I know for a fact that I do because I set it up this way intentionally. So here's A. Here's the voltage VAN. Here's ZW. ZY. And close our circuit, right? So ZW was given to us. ZY was given to us. VAN was not. So in order for us to figure out our line currents, it should be pretty obvious. Let me put the line current on here. That our line current IAA should just be our voltage VAN divided by ZW plus ZY. Ohm's law, nothing remotely fancy about this. Our only problem right now is that VAN wasn't provided to us, right? So we don't have our phase voltage. Instead, we were given our line voltage. So how do you think we're going to get our phase voltage if our line voltage at the source is known? So are you suggesting that the line voltage at the source and the phase voltage at the source have the same magnitude for a Y-connected source? You are mistaken. So let's prove it, okay? It's totally fine. This is a new thing to all of you guys, so mistakes are going to happen. That's great. Okay, so let's look at things here. Okay, so the line voltage at our source, at least for the A phase, is here, right? So I can write a simple Kirchhoff's voltage law equation around this path to relate my phase voltages, at least the A phase and the B phase, to the line voltage VAB, right? So I would have something like, let me just tuck it down here. So I can see pretty easily that negative VAN plus VAB plus VBN is equal to 0. Just from Kirchhoff's voltage law, right? Nothing remotely fancy going on. Now that we have that, I'm going to come down here and I'm going to rearrange that. So I'm going to put my line voltages on one side of the equal sign and my phase voltages on the other side of the equal sign. So VAB is going to be equal to VAN minus VBN. Just move stuff around. And recognizing that we have a balanced source, this is going to look like VAN minus VAN times 1 angle negative 120 degrees. We've already done this. So this is just VAN times √3 angle 30 degrees. Rearranging, then our phase voltage for a Y-connected system is going to be simply our line voltage divided by √3 angle 30 degrees, which should come out, and there's a little bit of rounding error here, to be 120 angle 0 degrees volts RMS. So very often when you're dealing with three-phase voltage sources, like if you were to go, and you could do this, might not be a great idea, you might get some funny looks, but if you were to pop downstairs here to the bottom floor of Bogart Hall in the stairwell and open up the breaker panel, which it's not locked, I know this for a fact because I used to have to reset the breakers pretty regularly when I was teaching in this building more often, because kids were just total jackasses using the heat shrink guns and all that kind of stuff. Too many of them at the same time when I was teaching the 120 series. They trip the breakers. Anyway, so if you go pop open that breaker panel, cover and all that kind of stuff, you'll see that it has a listing on the nameplate that says something like 120/277. The 120, so Bogart Hall has three-phase power because there are machines in here that require three-phase power. The 120 is the phase to neutral voltage, and the 277 is the line to line voltage. So those are effectively just depending on how you connect things to the internal circuits in this building, you have access to either 120 volts or 277 volts. Okay. So that's a very, very common voltage used here in the US. If any of you guys live in a large apartment complex, I'd be willing to bet your breaker box says the exact same thing. 120/277. If you live in a house, though, you have access to 240 and 120, not 277. And it's because single family residences use a split phase system, a split single phase system, as opposed to a three-phase system. But anyway, that's a topic for another day. All right, so now that we have this voltage VAN, our line current IAA is simply going to be 120 angle 0 degrees volts RMS divided by, so let's see, ZW plus ZY. So that's going to look like 5.1 plus J 2.05. Throwing that into a calculator. I get a current of 21.832 with an angle of negative 21.898 degrees amps RMS. So now to answer Toby's question, if I wanted the line current IBB, I could draw a single phase equivalent circuit for the B phase of my three-phase system and all that jazz. But because I'm lazy, I'm never going to do that. Instead, I'm going to take my magnitude, 21.832, and I'm going to just subtract 120 degrees from the phase angle. So this is going to look like negative 141.898. And this is the exact same answer that I would get if I was bothered to do all of the analysis, but why on earth would I? I can just shift it by 120 degrees to get the exact same result. The C phase would just be 21.832 with an angle of negative 261.898 degrees amps RMS. Just subtracting 120 from the phase angle again. Now, I want to be clear here. I'm going to use this convention where I'm allowing my phase angle to be larger in magnitude than 180 degrees in these three-phase systems. I definitely understand that if you took 21 the answer for the IAA, and you just multiply that in your calculator by one angle negative 240 degrees to get ICC, it's going to give you a phase angle that isn't negative 261.898. It's going to give you positive 98.102, which is just 180 degrees out of phase, or actually 360 degrees out of phase, right? It's the same exact angle, just your calculator is always going to give you something between negative 180 and positive 180. Okay, so I'm okay with using either convention. I just want you to be aware I'm always just going to be as lazy as possible and just take 120 degrees away once and then take 120 degrees away twice and call it a damn day. Because why make it any more difficult than that? All right, so we have our line currents. Now we need those line voltages at the load. How are we going to figure that out? Mm-hmm.
That. Define.
100% correct. Okay. So what Hayden has suggested, Holden, shit, sorry, thank you, is that we find this voltage VAN, excuse me, and then we use that voltage to get our line voltage that we're actually looking for. That is exactly correct, okay? So how might we find this voltage VAN? Well, we could either take our line current IAA and multiply it by ZY, which will get us that voltage, or we could have done voltage division, right? That also will give us the exact same thing. So because we already have IAA calculated, let's just go ahead and do that. So that's going to be IAA times ZY. So that would be 21.832 angle negative 21, hold on, 0.898 multiplied by ZY, which was, I think, 5 plus J2, if memory serves me correctly. If I got that wrong, please let me know before I type it into my calculator and look like a jackass. And I got 117.567 with an angle of negative 0.097 degrees volts RMS. From here, Holden, would you care to take a stab at what I'm going to have to use to convert? Because yeah, so this time, instead of dividing by root 3 angle 30, we're just going to multiply by root 3 angle 30, because that's our conversion factor between a line voltage and a phase voltage for a Y-connected thing, right? So VAN times root 3 angle 30 gives me 203.63 angle 29.903 degrees volts RMS. And from here, we could say that VBC is just going to be 203.633. Oh, goodness. So 29.903 minus 120. Negative 90.097. And VCA is, let me take 120 degrees away from that. 203.633 angle negative 210.097 degrees volts RMS. So hopefully I have imparted upon you how ludicrously easy this is for a YY system. Okay? We don't really have enough time to go into detail today for the other types of systems that we are going to face, but I'll tell you effectively what it is that we're going to be doing in our next class meeting. So instead of learning a bunch of different rules about how to analyze these other types of systems, instead we are going to learn transformations so that we can make a delta connected source look like a Y connected source, or make a delta connected load look like a Y connected load, so that we can just use a single phase equivalent circuit for literally everything, and then use the information we glean from that trivial analysis using KVL and KCL to figure out any quantity that we can't get directly from our single phase equivalent circuits. Okay, so that's what we've got in store for us on Monday, is just learning transformations. Technically, we kind of already have the source transformation down. It's just this √3 angle 30 degrees back and forth to go between delta and y, actually. We'll talk about that in more detail on Monday. All right, so hopefully most of you have noticed that your take-home exam is finally up. Sorry for being a jackass and taking so long to get that. While I put that up, I went ahead and put up your last 3 homework assignments for this class as well. They're all related to 3-phase circuits. Realistically, you could probably do, I think, 2 or 3 of the problems from homework set 14 now, because they're just YY systems. By the end of class on Monday, you should be able to completely do homework set number 14 and number 15, or maybe it's 15 and 16, whatever. The last one is about power stuff, so we're not there yet. Yes.
This last exam, aren't we allowed to make our own equation sheet again?
Yes.
Okay.
Yep, for this last exam, you are allowed to make your own equation sheet. And I'm going to endeavor to actually just go ahead and put your take-home portion of exam 3 up this weekend, or excuse me, exam 4 up this weekend, so that it can be due on the last day of the quarter or something like that, so that you're not having to work on things after the quarter's over. So anyway. All right, go away.